question about the respiratory system. So we know that external respiration is this movement of gases from the alveoli to the blood, and the blood to the alveoli. That is the responsibility of the respiratory system in terms of moving gases. Yeah, so we haven't really talked about the movement of our fluid, movement of gases between the blood and the interstitial fluid, but of course you know that interstitial fluid is found everywhere. And so we don't just move the gases from the tissues to the blood, we have to get through interstitial fluids as well. It's a minor point in my mind. More important that we understand this diffusion rate and why the diffusion happens. Concentration gradients drive our diffusion. And remember the difference between your external and internal respiration. External at the lung level, internal at the tissue level, right? We see this amazing ability. Look at these, the pulmonary capillaries. It just takes a quarter of a second for oxygen to be loaded into the blood and for CO2 to be offloaded from the blood to from the tissues to the blood, right? Pretty quick. If we have increase in our respiratory rate, as in exercise, we're going to see a change in how long it takes our erythrocytes to be moving through the system. If it takes just 3/4 of a second to travel through the capillary beds at rest, it takes just 1/3 of a second to pass through. And that's important to remember because we have to be able to link our ventilation and our perfusion. We have to be able to perfuse at the same rate that we can ventilate. Otherwise, we get out of whack. And so we have multiple factors, as this says, that are responsible for our external respiration. The first two are dictated by a guy named Henry's law. Henry's law stipulates that partial pressure gradients are very important. And Henry's law also stipulates that solubility is very important. Interestingly enough, CO2 is much more soluble in fluids than oxygen is. What do I mean by that? It's going to diffuse more quickly into the blood, and oxygen is going to take a little longer. Oxygen is not as soluble. However, we don't worry about that so much because the partial pressures are not dependent on solubility. And so when this says that partial pressure gradients are important, what that's talking about is the pressure that a gas is exerting on in the volume or space that it's contained, regardless of what other gases are present. So it could be the only gas and it would have the same pressure expansion gradient than if it were loaded with water gas, CO2, nitrogen, and any of the other gases that might be presented to the respiratory system. But together, partial pressure gradients, solubility coefficients are going to determine how our CO2 and our oxygen are moved through the system. And believe it or not, in the end, even though CO2 has a greater solubility coefficient and a lower partial pressure, these two equal themselves in the blood. And so we're just going to remember that Henry's law stipulates that partial pressures and solubility are very important in how we get gases to and from the lungs to the tissues, and from the tissues back to the lungs. And you know this because everybody's drunk a soda here and there, right? You can carbonate a fluid, but when you open it up, where's that CO2 going to go? Out. Why? Concentration of CO2 in the fluid versus the air. Henry's law stipulates that our partial pressures are going to be determined by where those pressure gradients are seen or found. So this graph right here is looking at the atmosphere and the partial pressures of oxygen in the atmosphere and the pressure gradients of oxygen. All right, so let's look at this. So this is a very steep gradient. And this very steep gradient is a result of something called a hyperbaric chamber. Have you heard of those things? Where have you heard of them?
Ocean
Yeah.
pressure stuff. Like,
Somebody dives down too deep. They come back up too fast. They've got carbon monoxide in place of carbon dioxide. And they also have nitrogen gas. The nitrogen gas causes things called the bends. So these people that have come up too quickly and have not been able to dissipate the CO2 from their, and they get nitrogen that blocks things up, they're put in a hyperbaric chamber, because the hyperbaric chamber is going to deliver 100% oxygen, which is going to force that CO, carbon monoxide, or the nitrogen gas out. Also, they'll use hyperbaric chambers, and I didn't know this, but if you have gangrene, gangrene is a result of an anaerobic bacteria, meaning doesn't like oxygen, you're going to be put in a hyperbaric chamber to drive that carbon monoxide out from the hemoglobin.
seems like it would be painful.
But aren't
Yeah.
hyperbaric chambers also used therapeutically? Like, a lot of people just go for the treatments.
To get increased oxygen
Oxygen.
load.
Mhm.
I imagine there are probably athletes that like to do that, right? Get a little extra oxygen in their tissues. Yeah?
Is that the same would work like gangrene, like foots
Yes.
for like
Yep. Dead
diabetic
tissue,
people?
necrotic tissue. Yep. So we got hyperbaric oxygen therapy, 100% oxygen delivered, very steep, rapid diffusion of oxygen. Here's our normal gradient of oxygen. Normal, right, 158 partial pressure of oxygen in the air. I'm going to talk about that in a moment. Here is reduced gradient of oxygen, so much slower diffusion of oxygen at 300 meters or 10,000 feet. Have you ever climbed a hill, increasing grading in altitude? What happens?
It does not very good.
It's so hard.
It's also really scary.
Hard to breathe, isn't it? Why is it hard to breathe? Because the partial pressure of oxygen is reduced. So you are, one, fighting to get more oxygen in, and two, because you are exercising, you're producing more CO2. So your ventilation rate is going to increase because of this slower gradient of oxygen diffusion. Now, they're going to move from higher pressure to lower pressure. We understand that, those two gases. There's another law, Dalton's law. Dalton's law says that each gas exerts a pressure equal to its amount. What does that mean? Well, so our partial pressure of oxygen at 160 millimeters of mercury is about 159 millimeters of mercury. Keep that in mind. In the air, our oxygen actually occupies 21% of the air. So the air we're breathing is 21% oxygen. The air we're breathing is 0.04% carbon dioxide. The air we're breathing is, look at this, 78.6% of the air that we take in and push out is nitrogen. What do we do with nitrogen? Do we need nitrogen? I would say so. But how is it we have all of this nitrogen and we don't, it's inert.
Because it's not.
It's not available to us.
Oh, okay.
The reason we eat plants and other animals is because we need the nitrogen that they've converted for us. Because the gas is inert. We can't access it and use it. But we need nitrogen for lots of things.
Yeah, because nitrogen's a noble gas, right?
I don't remember the term noble. What is noble?
That doesn't conveniently have the periodic table
Yeah,
constant somewhere.
no. We're not going to worry about that in a moment.
It's just take them out.
All right, so how did I get this 20.9%? Well, what I did was I took 159 millimeters of mercury and I multiplied it by 760 millimeters of mercury, and I got 20.9%. Or I didn't multiply, I divided it to get the 20.9%. Water, 0.5%. Water is a gas, remember? In, out, in, out, in, out. All right, so we have our partial pressures and how those pressures are going to be changed based on altitude, based on function of your body at any given time. Now, this is a very interesting, and this will probably be the last thing we get to talk about today, diagram about expired air, the contents of expired air versus inspired air. Let's take a look. So in inspired air, we have a partial pressure of oxygen at 159 millimeters of mercury, partial pressure of CO2 at 0.3 millimeters of mercury. Our expired air is partial pressure 160 millimeters of mercury of oxygen, 32 millimeters of mercury of CO2. Why do we have a difference there?
Because one is active and
We take that oxygen in, we use it, and then we send some back out. So you remember me talking about how we're constantly moving airs back and forth. There's always a mixing of gases within the system. So if we inspire 159 millimeters of mercury, we're going to expire 116. What about this difference? 0.3 versus 32.
There's not much in there.
Yes, so CO2 in, not so much, but CO2 out, because that's what we're expiring. So we have alveolar air, a partial pressure of 104 versus partial pressure of 40. Why is the alveolar air so different to the inspired air?
the exchange between oxygen and carbon dioxide once you get into the lungs.
Yep, we're going to see CO2, the oxygen is going to be decreased, and the CO2 is going to be increased because we're delivering CO2 to the lungs, and we're seeing a decrease in the alveolar partial pressure because we're taking oxygen out. But also we have a mixing of air there. Again, mixing of air. All right, so at the oxygenated blood, we have partial pressure 95 millimeters of mercury, CO2 40 millimeters of mercury. Why is this so much lower than in here?
Because you use some of it.
Hmm?
It was utilized in like alveolar tissue.
Yep, and moving that stuff around, so tissues are durable. Right. Why is the partial pressure of oxygen in arterial blood different to that of alveolar blood? There's another reason for that. And this is the most fascinating part of all, I think. So the oxygen, we see an oxygen dilution factor, 104 to 95. The reason for that is because we are going to see a mixing of blood from the pulmonary veins. What are they bringing? What do they carry?
Oxygenated.
Freshly oxygenated blood, pulmonary veins carrying freshly oxygenated blood. They're going to they're going to join up with blood in the bronchial veins. And the bronchial veins are the veins that are taking deoxygenated blood from the respiratory system tissues. Because remember, the blood that is going to the lungs from the heart is strictly going to the lungs to pick up oxygen, drop off CO2, come back, deliver that oxygen to the heart so the heart can send it out to the rest of the body. The bronchial vessels are providing oxygenated blood to the lung tissue and providing oxygenated blood to the trachea and the bronchi and all of those smooth muscle cells that are in the, right? They need to be fed too.
That threw me off with the heart when we studied that. The coronary supply versus what's going in the heart. Same with the lungs, it makes a lot of sense.
Exactly.
Because the
You have to
tissues
take care of the
also need it.
tissues of the organ themselves.
Yeah.
And so that's why we see this difference here. Okay, guys, that's perfect timing. Where are we? So we're going to finish this up pretty quickly on Wednesday and then break into the digestive system. And I really appreciate it if you look